Alright, welcome back. We are going to be doing section 2.6, Moments and Center of Mass, for the next couple of videos. This will be part 1. So what we're going to learn, and this is clear throughout all of section 2.6, so we'll learn how to find the centers of mass of objects distributed along a line. We will locate the center of mass of a thin plate, and that's where the calculus will start to show up. And we will also use symmetry to help locate the centroid of a thin plate, which centroid is pretty much the same as our center of mass. So looking at these objects that we have here, this first object, A, this is just saying that we have something that we're trying to balance. So we've got a line, and it's just one-dimensional, and our center there of balance. Then what we can come along doing, we can put a mass on one side, a second mass on the other side, and the distance that you put the masses away from the center of balance is going to have a big impact on the balance of the beam. So if you think of like a teeter-totter, if you have two kids that weigh the same and you put them each at the very end of the teeter-totter, then it would balance. If you moved one child in, keep moving them in, the more off balance it's going to be. Or you may have done a teeter-totter before where you have one child that's bigger than another, and you can change the fulcrum, or the center of balance of that teeter-totter, and you can move it closer, farther out, for the child that is smaller is going to have the longer end, and the child that is bigger is going to have the shorter end. All of that has to do with what we call a moment. So I'm going to go switch screens here real quick, and we're going to go to PhET-Lab. This is from Colorado University, and you'll notice that I've used some images from this in our notes as we go along. So if we take a 5 kilogram brick and we put it at a position of 5, let's say, feet, right? So that's going to be 5 feet away from the center of our balance. And what am I going to need to put on the other side to make this balance out? I could put 25. No, I could put another 5 kilograms at 5 here. Of course, obviously that would center it out. But we want to look at what happens with different sizes and to be able, and the distance as well. So the moment that I have on here right now is I have 5 kilograms times a position of 5, which gives me 25. So this here is going to be what we consider a moment of 25. So I also need to create a moment of 25 on the opposite side to get that to balance out. So I'm going to take a 10 kilogram brick and I'm going to put it at the position of 2. That's going to give me a moment of 20 on the left hand side. Then I'm going to take a kilogram of 5, or a brick of 5 kilograms, and put it at the position of 1. That's going to give me a moment of 5 here, plus another moment of 10 times 2, which is 20. So now my left-hand side is a total of 25 moments. So on each side, I now have 25, and when I flip this switch down here, and my columns disappear that are holding up my balance beam, it balances perfectly. Now let's see what happens if I would have taken this 5 kilograms off. If I take that 5 kilograms off, it's no longer balanced. If I take this 10 kilograms and move it down to the 3, then I'm off balance the other way. So our position of each brick plays a huge part of whether or not we are balanced. There we go. Now if we were in class, I would love to give you guys this website. I may put the link to this website in on my Open Math so that you guys can click on that and play. See, there's some games that you can play down here. Yeah. Anyway, it's a really, really cool website. So I might put the link to that if any of you guys want to look at that. Okay, back to our notes. Alright, so in our notes, we identify X bar as our center of balance. That's going to be identified by X bar, so I'll give you the equation for that. And then remember in the simulation that we just did, to find each moment, we took the weight of the mass times its position to find that moment. Now when I'm doing them all together, what I'm going to do is I'm just going to add all of the moments together. I'm not even going to worry about, what's on the left-hand side, what's on the right-hand side, and does it balance? Because now what we're looking at is I cannot move my masses. My masses cannot move. So where would I have to move the fulcrum, or the center of balance, to make it balance? So now that's what we're trying to find. We're trying to find the center of balance, x bar, if we include all of the masses and all of the positions on our line. All right, and this gives you the mathematical reasoning for this. So m sub 1 is the weight of the mass. Then in parentheses, they just have the distance. This is all just saying, what is the distance between x bar and x sub 1? Right? X bar is our center of balance, so both the mass times the distance are going to equal each other. So if we were looking at this picture, this mass must weigh more than this mass over here. Okay, and so then just following through here, they have rewritten this, since we know that x sub 1 is going to be a negative number and we want that to be absolute value. They switched that around and took the absolute value bars off. X sub 2 is larger than x, because we're imagining we're on a number line. So that will never be negative, so now we can get rid of those absolute value bars. And then multiplying the mass size through, and the x bar is what we want to solve for. So we're going to get everything with an x bar on one side, everything else on the other, and factor out that x bar. Then we have x bar equals m sub 1 plus m sub 2. Well, what is that? That is the sum of all of the masses, and this can be done with multiple objects. So this is going to be the sum of all of the masses. Then on the right-hand side, this is the mass times the distance, plus the mass times the distance. Now remember I talked about that being a moment. So what we have on the right-hand side is we have the sum of all of the moments combined. It doesn't matter if they're on the left-hand side or the right-hand side of the equation. It's all of the moments combined. So when we get down to our final equation down here, we have x bar, which is the center of mass, is equal to the sum of the moments, all moments, over the sum of the total mass. So just the total weight of all of the objects put together. And that's how we find the center of mass. All right, so here's all of our equations written mathematically. So the moment of a system is what we most commonly refer to as a moment. That's going to be represented by a capital M. So our moment is equal to the sum of the moments times the distances. The total mass of the system is going to be denoted by a lowercase m, and is just like it says, the total mass, so out of all of the masses. Then the center of mass is identified by x bar. So the center of mass of the system is the point at which the total mass of the system could be concentrated without changing the moment. So if we cannot move those moments, let's say they're kids on a balance beam or on a teeter-totter, if we can't move those kids, we would have to move the teeter-totter to the left or right to get it to balance if they were different weights or in different positions. So if we cannot move those, we want to find the center of mass. This is how we would do it. We would have x bar is equal to the moment over the total mass. And those will be the equations that we use. And then, once we move that up a step and say we can do this with multiple masses on our number line, this is how we would have to denote it with our summation rules. But same as what we said before, it's just going to be a continuation of this equation up here. So m sub 1, x sub 1, plus m sub 2, x sub 2, plus m sub 3, x sub 3. We would just continue on with how many of our masses we have. And that is all that they're saying here in this equation. So this right here, lowercase m, this is the sum of all of our masses. Capital M is the sum of all of our moments. And then the center of mass is the moment over the mass for each situation. Okay. One other thing that you will see in the homework, this is not in the OpenStax book, but it is in the homework. I had to do a little bit of research to figure it out, but I finally did. So the moment can also be moved about a point other than the origin. So So when we are looking at a moment, that's always assuming that we are centering that around the origin. Because remember when we looked at the distance, we always took that distance from the origin. So we can also do that. So everything that we've done above is in terms of the origin. We can also do this in terms of a different point. So the moment about x equals p, we're going to denote as MP. A moment about the origin would be MO. So when the moment is moved about a different location, P, than the origin, then we're going to use this equation. So the moment about a different point P is equal to the original moment, or the moment around the origin, minus the total mass times P, or whatever point they want to give us. So you will also have to use that equation. Okay, so we're ready for our first example. So 3 objects are on the number line. Enter each answer as a whole number or 2-digit decimal. So I put a little picture here, and I used that. So a mass of, oh, my little things didn't follow through. Shoot. Okay, so when I printed this out, my pictures, I put different grams on there so they would all match up. So we'll have to write them in here. Okay, so this is a mass of 6. It should be a 6 there. This should be a 3. And, oh no, that was not right. At 5 we have 7. A mass of 5. That was right. At x equals 5, we have a 3. At x equals 1, we have 6. At x equals 7, we have 5. Okay, there we go. Alright, so this kind of just gives you an illustration of what we're looking at. Each one of these masses is shown, and the positions is shown. And so first thing that we want to know is what is the total mass. Oh, shoot, that should be a lowercase m. Okay, the total mass, m. So m is equal to 6 plus 3 plus 5, which is equal to 14. The moment about the origin, so we have our moment, our capital M, and we are going to be going around the origin at this time. So it's going to be equal to 6 times 1 plus 5 times 3 plus 5 times 7. And that's going to be considered our moment. So this is just taking into account all of the masses and the distance that they are away from the origin. So now we have 6 plus 15 plus 35, so 30, 40, 56 is going to be our total moment in terms of the origin. So then the center of mass, which is our x bar, is going to be, x bar is equal to the moment over the mass. So that's going to be 56 over 14. Now up here at the top is that it either wants a whole number or a 2-digit decimal. So ours is not going to end up being a whole number. So let's go ahead and do that division. So 56 divided by 14, and we have 4. Alright, so x bar is 4. That's our center of mass. So if we go up here and look, our center of mass is going to be at the position of 4. Right there. And so that would be perfectly balanced. And so what we would say there, if an object is perfectly balanced, then its moment is 0. That means that the moments on each side, if we look at them individually, they would equal each other. So we have, let's look at our individual moments. We have 5, well, yeah, we won't look into that yet. It would be 5 times 3 here, because we would now say that this is our origin. So it would be 5 times 3 is 15.